equilibrium partial pressure of substance in vapor phase divided by mole fraction of a substance in that solution. Right. Actually, we talk of that vapor component of that solution, which is in that system. Normally, we call it y over x. That, for instance, I have a component A, and it has how much vapor mole fraction compared to its liquid mole fraction, right? So it will show us its volatility. So if it has higher number in vapor pressure, or you can say partial pressure, it means it will have higher volatility, because volatility is totally depending on partial pressure of that component. And that partial pressure is coming from where? Definitely that is coming from the vapor pressures. So we can call it the vapor partial vapor pressure. So the formula can be partial pressure of component, partial vapor pressure of component A divided by mole fraction of component A in that solution. Right. So this is how we can calculate volatility of any substance. I think we might have done some problems on that in earlier lectures. If we didn't, that's no issue, because that's just a generic or basic concept. The volatility of a material in the pure state is equal to the vapor pressure of that material. Yeah, if we talk about a material or any substance which is in the pure form, so its volatility will be equal to its vapor pressure, but that is in the pure form. When it is not in the pure form, it means that if you're going to add few more components into it, if it's a mixture, now their properties will deviate definitely. So now we talk about the relative volatility. Relative volatility is all about relating volatility of a component A with component B or others. Right? Means we are relating volatilities with different components. It means the system must have more than one component. It cannot be based on one component. If it's just one component, we call it volatility. But it is more than one component, then we can call it relative volatility. Relative volatility of A with respect to B, relative volatility of A with respect to C, relative volatility of C with respect to D. So this is how we can relate the different volatilities. Here you can see an example. We have a mixture of component A and component B. This is how we can relate the volatilities. Now how we do it? Actually, we divide the volatilities. For instance, whatever the volatility of component A is, if that's divided by the volatility of component B, this is going to give us volatility of component A with respect to B, or you can say volatility of A relative to volatility of B. In case both have the same volatility, so what are we going to get? For instance, if I say the relative volatility of component A is 0.5, and similarly volatility of component B is also 0.5, so I'm going to get answer of unity. That's 1. That means that the relative volatility is the same, right? So if relative volatility is 1, there would be a major hurdle for you in separating the components. You cannot separate them. So that is an important thing. There must be some relative volatility. It means that volatility of one component must be different than the volatility of other component. If they both have similar or same volatility, you cannot separate them. So that alpha is going to define that which component is more volatile, and this is how you can. So this is one of the important factors you can say in distillation. Okay, talking about vapor pressure, it is defined as the pressure exerted by a vapor and thermodynamic equilibrium with its condensed phase, solid or liquid, at a given temperature in a closed system. The equilibrium vapor pressure is an indication of a liquid's evaporation rate. Yeah, actually, this is pressure of vapors. When we talk of vapor pressure, actually we relate it with any system of the same component which has some you can say part fraction in liquid or in solid, and other is in vapor. If it's totally vapor, then we do not need calculate vapor pressure because we already know that that component is in gaseous form, right? We talk of its vapor pressure because we know that some of its fraction is still in liquid or solid phase. And definitely that vapor is in equilibrium with that liquid or solid. We normally call it the thermodynamic equilibrium. It is a dramatic study of transformation of matter and energy in a system as they approach equilibrium. The word equilibrium implies a state of balance. I hope you all know that. Okay, talking of an azeotropic mixture, normally we call it the constant boiling mixture of a special composition giving a minimum or maximum boiling point, then individual component with minimum or maximum boiling respectively. Now, what happens in isotope mixers is actually either they lower the boiling point of the system or they, raise the boiling point of the system. So there cannot be a bigger difference in boiling point of, mixture components. For example, if I have component A and B, or you can say two components, their vapor pressures would be, more or less similar. Either they will be lower or they will be higher. In both cases, we always have difficulty in separating those components. Normally, at such situation, we call that constant boiling mixture. Here is one of the example, mixture with maximum boiling point. The mixture containing 20.2 ml of HCl and 79.8 ml of water. Now this is a maximum boiling point. Mixture of minimum boiling point. Mixture containing 95.9% of alcohol plus 4.5% of water. Now, at one mixture, you can see they are at a maximum boiling, and I will be explaining that in detail for some of these students, especially for section B, because in A we already have gone through this minimum and maximum boiling concept. Okay, a little revision of Raoults law. It expresses a quantitative relationship between concentration and vapor pressure. It states that partial pressure of each volatile constituent is equal to vapor pressure of pure constituent multiplied by mole fraction in solution at a given temperature. How this happens? Let's go through its mathematical equation. Suppose you have a homogeneous mixture of component A and component B. The partial pressure of component A in the mixture would be what? It would be actually is partial pressure in its pure state multiplied by small fraction. That's very simple. This is how you're going to calculate partial pressure of any component. And mainly that mixture is the solution is ideal, because if that is ideal, this is going to get the concept of this one, that their partial pressures do not change when they are in mixtures, right? So their partial pressure in their pure form multiplied by their mole fraction will give us the partial pressure of that mixture, that component in the mixture. Here further you can see that mole fraction of A in solution, that is XA. Vapor pressure of A in pure state is P dot A. Partial pressure of component B similarly, that would be PB multiplied by XB. This is how you're going to get partial pressure of B in the mixture of component A and B. Total pressure will be given by partial pressure of A plus partial pressure of B. They are going to give you total pressure, which is here PT. You can see that. And if we add the above equations, which are equal to PA is equal to POA multiplied by XA. Similarly, PB is equal to POB multiplied by XB. So the last equation at bottom, you can see this is for total pressure of that mixture. Okay, here you can see a detailed example of that Raoult's law, that how this can happen. How can you calculate total pressure of the system and individual pressures of system based on their partial pressures and based on their mole fraction. Okay, let us take 2 points here. At left side, you can see we have the benzene, right? At the right side, you can see we have the ethylene chloride. Now, ethylene chloride at right side, you can say, has a mole fraction of 1, right? And the other side, uh, that XB, if that's the benzene, it has mole fraction of 1, right? So we have two ends, right side and left side, right? If we talk of component A, now component A, can you see my cursor? Raise your hand if you can see my cursor so I can move on. Okay, let me set this up first. Okay, it means you can see my cursor. That's fine. Okay, now if you see here, that's actually a component A, you can say. So concentration of A here is 0 because here XB is 1. When XB is 1, definitely XA will be 0. So here you can see when XA is 0, their partial pressure is 0 because mole fraction is 0. It means there is no component, no mole fraction of component A at this side. Okay, if we are going to add some mole fraction to A, if you see this graph, this is going up till this position, which is, you can say, the maximum partial pressure of component A in the pure state. Here also you can see that's PaO, which is showing that it's a partial pressure, a vapor pressure in the pure state. We cannot say it's a partial pressure actually. Now it's a, because pure, so we can say it's a vapor pressure in the pure state. So 236, you can say mmHg is actually a vapor pressure of component A in the pure state. Now here you can see small fraction is 1. When a small fraction is 1, it means that it's in pure form. Similarly, if you come to the other component, which is component B. Now here is mole fraction is 0. When a small fraction is 0, definitely its vapor pressure or partial vapor pressure will be the 0. Now if we go left to top of that, we will find a value at the end of that graph, that is 268 mm of Hg. Now this is showing PbO. This means that this is the vapor pressure of component B in its purest form. Now these are two extreme ends, where you can see different uh, partial pressures of two components. Now, if we talk about a system, now here you see the total vapor pressure at top of that graph. That is actually total vapor pressure of the system. Okay, for instance, if I am here, at this position, right? If I'm this position, let me do something different for you. Let me take out snip tool for you so that I can do, some rough work here. So that might be more easy for you. Oh,
Sir,
okay.
recording started.
Recording is not available.
Not, sir.
Okay, maybe somebody did their work, but I have put on recording again. Okay, here you can see on my snip tool that what I have done. Now, if you see at this position, now this is, purest form of component B. You can say that it is a vapor pressure in its purest form of a component B. Similarly, at this position, you can say that it is the pure vapor pressure of component A in the purest form. So these are two different values, right? Because here you can see that XA is definitely what? It is of course 0 because XB is already 1, because we know that total mole fraction would be sum of mole fractions of what? Component involved in that system. If we have two components like A and B, there are some they will always be 1 because they are in fraction. Now, if xb is 1, definitely xa will be 0. Means that B is in the purest form. When B is in the purest form, we can say that it's partial pressure in the purest form. Similarly, if we talk at the right side, when we have A, now this is the partial, not partial actually, because when B is 0, it is not partial, it's totally pure, A is totally pure. So the vapor pressure of component A in the purest form would be 236 mm Hg. Now, these are two values at two extremes. We are talking about at minimum and maximum when they are at their purest state. But if we talk of a system in between, for example, if you're talking about disposition when mole fraction is zero point 0.5, zero point 0.5, right? So now here values will be definitely different. Here is something interesting. You can see that total pressure in purest form for A is 236 and for B is 268. Definitely, it means that vapor pressure of B is higher compared with A when they are in the purest form. So now here value will be different. Now if you look at this graph, actually this graph is showing total vapor pressure of the system, right? So we can calculate partial pressure of any component at this point, any component at this point, either of component at this point. At any point we can calculate this by using Raoults law, because we know that if we are going to have mole fractions in partial pressures, we can calculate partial pressures as well as mole fractions given what we need to calculate. So it depends, you know Okay, so I think that's enough for this Raoult's law. We are moving ahead. Now we are talking about positive deviation and negative deviation. That how these things change. These are actually happen in real solutions. When we talk of ideal solutions, there is no deviation. You remember that, right? So this means we are talking about more of real solutions. Positive deviation in some liquid systems, the total vapor pressure is greater than the sum of the partial pressures of the individual components. Right. Okay, this is one of the examples. Benzene and ethanol differ in their polarity, uh, length of hydrocarbon chains, and degree of association. So there are several things that can help those components to deviate. I hope you remember about activity coefficient. Actually, this deviation is called activity coefficient, right? When activity coefficient is higher than 1, now higher than 1 is means that it is positive deviation. If that is lower than 1, it means that would be negative deviation. Actually, that is changing, right? So it depends that how system behaves. If your activity coefficient is bigger than 1, you can just a positive deviation. It means that now the vapor pressure of that system has increased actually, right? For example, I'm just giving you an example. Let me take you through again that snip tool. For example, we are talking of the same system of A and B. When they are ideally, for example, this is 268 and this is 236, and if we have zero point 0.5 mole fraction of each for this one like 268 and plus zero point 0.5 of uh, this one 236. Now if a solution is ideal, right? If solution is ideal, so their total pressure should be the same as of this one. Remember, right? If you are going to calculate whatever that answer is, but if it is not ideal solution, it is deviating, then there can be two things. Now this value can be different than you know uh, than the measured value, right? If this value is like, for example, this is actual in ideal condition, you can say. Can somebody calculate this one, or do I need to do it myself?
Sir, 237.
237. Okay, 237 actually should be ideally, right? Okay, or you can say actual somehow. Now, if we are measuring it with any equipment, we have, any gauge which can measure the vapor pressure. And that vapor pressure is, for instance, 240. What will be answer? Definitely it will be bigger than 1, right? In this case, you can say the deviation is positive because vapor pressure of system has risen, that has gone up. But something can happen inversely. Now, if we are measuring this one and that vapor pressure is not 240, actually that is 230. Now, this should have been 237. Now, this is a negative deviation because answer is less than 1. Is it? When it is less than 1, this means that this is a negative deviation. I hope you got what I'm trying to say. Okay, this is how we calculate the positive and negative deviations. Normally we call that activity coefficients. In negative deviation, some liquid systems, the total vapor pressure. Okay, give me 1 second, guys. Okay, I'm back. Okay, this is how we calculate or go through positive or negative deviations. As remember, this is always for real solutions. Ideal solutions cannot deviate. Okay, in some liquid systems, the total vapor pressure is lower than that of the sum of the partial pressures of individual components. Examples, chloroform and acetone, due to hydrogen bonding, salt formation, and hydration. So you can see the reasons as well that why those vapor pressures get lower or get higher. That's totally because of the bond association, some of the bond energies, as well as we can say that electronic power on those components. We can say even the hydrocarbon chains can affect, and degree association can also affect this deviation. Okay, graphically you can see here that how the system can behave. Now, there are two graphs you can see. One is at the left side, other is at the right side. First, let's talk about the graph at left side, which is 5.3 vapor pressure of system showing positive deviation from Raoults law. If you look at top, you can see that how, okay, I think I have this one. Okay, this can work. Okay, if you see at the top, because ideally this should have been the vapor pressure, total vapor pressure of the system. But in fact, what has happened is when you have gone through the system, it has changed. So now this is above the line which is actual vapor pressure of the system. This means that it has risen from the actual, right? So this graph is showing total pressure of the system which is more than the sum of partial pressures of those components, right? And in the second graph you can see now this graph here is lower, this one is going here, right? So now if you can see here, the total vapor pressure of the system is decreasing, as I have given you earlier examples that how that can decrease. Now this one is a negative change and this one is positive change, but in both cases distillation is going to suffer. Remember, it's not a good sign. Okay, that's just a basic lab scale distillation assembly, that how we distillate different compounds. If you see in this one, I think that's very basic. That might, you have done some experiments on it. I hope. If not, I think you have done nothing about this. Okay, let us talk about, first that's about this apparatus. Now, this apparatus is actually called the distillation flask. That can be of this shape or this can be of any shape. Now, what we do is we need any heating mechanism need to heat this one. If you see here, this is a Bunsen burner. Normally, we carry out such things in our labs. If you're going to heat this liquid, this will boil. When it is boiling, some of the vapors will leave this flask. When they are leaving, what we need to do is we need to collect them if we are going to carry out any distillation experiment. So what we need to do? We need to add a condenser. So here you can see you have a condenser. So how condensers? Normally what we do is we use a coolant. Water is a good coolant normally, because if we talk about tap water, its temperature is about 30 degrees, you can say, on average. When you're boiling any component, that might be at 60, 70, 80, or 100, depending upon the boiling point of that component. So water can work, but even if that is not working, it means that vapor pressure of your component are very high, or it's boiling at very low temperature, then maybe you need to use cooled water or any better. Can you please turn off your mic? Okay, you have a condenser that will be condensing your vapors of the substance that you have boiled. And definitely what you're going to do is you need to collect that one using a collector, you can say. Okay, sorry for the disturbance, guys. I just had to turn it off. Okay, I'm trying to use uh, actually that cursor. Okay, okay, this is a PowerPoint presentation. Okay, so we had talked about distillation assembly, that how it happens at lab scale. So these are the major components, you can say. In this equipment, you can say that it has that heating mechanism or heating system, you can say, and the column or the flask itself, and then you have condenser, and then collecting apparatus or vessel, you can say. So these are the major things, and then it has definitely its assembly, but that's just at lab scale. If you haven't done this experiment, when university is open, please do come, at least carry out a such small experiment just to see that how distillation works. Okay, general equipment for distillation, definitely you need to have a vessel or a still or anything in which you need to vaporize your system, your mixture. It is a vaporizing chamber, definitely it is, and used to place the material to be distilled. The still is heated by a suitable means of vaporization of volatile constituents. Uh, on laboratory scale, round bottom flasks made of glass are used so that progress of the distillation column can be noticed. A condenser is attached to the still using the appropriate joints. A trap is inserted between the distill flask and the condenser. So this is how a small distillation assembly can work. And then we talk of the condenser used to condense a vapor. It is kept cold by circulating water, air through jacket. And then there can be several types of condensers. Some of them are surface condensers. We call them straight tube, bulb tube, spiral, coil shape, double surface condensers, multi-tabular condensers. The condenser is connected to the receiver through a suitable adapter. So this is how condenser works. These are some of the examples that I already mentioned. You can see different types of condensers. Actually, you can say the type of condenser come from the inventor or from the company, how they manufacture it. So you can say it totally depends on the surface area that they are going to provide, and the contact time they are going to provide for vapor in that cooled liquid. More they are intact, more they are in contact, there will be higher heat transfer. You remember that, right? Even the mass transfer, we always talk of surface and contact area and contact time. If you're going to give it more surface area, more contact time, there will be more higher, higher mass transfer. So similar goes for the heat transfer. So these are nothing but to provide, some contact time and surface area between two phases, which are vapor and liquid. More they have time, higher will be the chances of condensing that vapor. Right, and this is indirect cooling. Remember, it's not direct cooling. You cannot add, water to those vapors. So it has a jacket. In jacket, there would be, one. You can that is whatever that tube is, inner tube and outer tube. Normally, you have gone through shallow tube heat exchanger. It's almost a similar concept that how condensers work. And then you have a receiver. Receiver can be any tank which needs to receive your liquid. I'm not going in details of the receiver. These are some of the examples that how receivers can be. Receivers can be, if you have a batch experiment, they can be in a batch. If they are in a continuous, so they can be in continuous. Now here, if you can see, actually these are the you can say that for the continuous processes when they have inlet as well as outlet. Okay, classification of distillation methods. Now, this is the work that is new to you because earlier all those things have been already discussed, majority of you in different classes. I'm still confused about my, PPT. I don't know why it's not showing properly, although it have should been like, better. Let me check it again for you. I don't know why, because it should not be like that. Please turn off your mic. Please turn off your mics. Whoever has put on mic, please turn it off. Okay, whatever problem I'm facing, but I'll sort it out. Okay, I'm using this again. Now, these are the actually things that we need to discuss in detail because earlier things were basic things for you. Some of you have already gone through that. Okay, let me use pen so that it is easier for me to do for you. Okay, so we have different types of distillations. We have simple distillation. We normally call it differential distillation. We have flash distillation. We call it equilibrium distillation. We have vacuum distillation. Normally it operates at reduced pressures or lower pressures. And then we have molecular distillation. We call it evaporation distillation or short path distillation. We have fractional distillation, and we have isotropic extractive distillation. We have steam distillation. We have destructive distillation, and then we have compression distillation. So these are the different types of distillations that we will be going through today. Let us talk about simple distillation first. It is a process of converting a single constituent from a liquid or mixture uh, into a vapor, transferring the vapor to another place, and recovering the liquid by condensing the vapor, usually by allowing it to come in contact with a cold surface. This process is known differential distillation. Uh, a, a distillation is based on the difference in volatilities and vapor pressures of the components of the mixture. So that's one of the simple, concepts about the simple distillation. Now, if we talk about this principle, liquid boils when its vapor pressure is equal to atmospheric pressure. We all know that how liquids boil. Simple distillation is conducted at its boiling point. The higher the relative volatility of liquid, better is the separation by distillation. Heat is supplied to the liquid so that it boils. The resulting vapor is transferred to a different place in condenser. So this is the basic principle of simple distillation. Normally, we do it at boiling point. First and foremost, there should be relative volatility difference. If there is not much or less, Then we will have complexities in distillation. Once that liquid is evaporated, heated, then you need to collect those vapors, in a different equipment. Construction, it consists of a distillation flask. You already have, I think, seen this one. It's almost a similar thing that you have seen here, right? So what you need to do is you need to boil it here, and this is going to vaporize. When it is vaporizing, you need to collect those vapors using a condenser, and then you have this assembly, and then this you have the collecting flask, you can say. So that's a simple construction for a simple distillation process. Of course, this is not a distillation column. You can make, generate, or build up a distillation column based upon simple distillation. But normally we don't. Okay, let's talk about working. The liquid, I think it's the same. I do not need to go through this. That's almost the same thing that you need to read about. Uh, so I'm not reading it for you. Okay, now let's talk about its application for the preparation of distilled water for injection. Volatile and aromatic water are prepared. Organic solvents are purified. A few official compounds are prepared by distillation. Examples are spirit nitrous ether and aromatic spirit of ammonia. Non-volatile solids are separated from volatile liquids. So these are some of the examples of its applications that where it can be used. So it's totally actually fundamental. It's totally, even you can do this at home. This does not need biggest things to carry out. So that's why we call it the simple distillation. Now talk about the flash distillation. This might be a bit new concept for you if you haven't gone through this. Flash distillation is defined as a process in which the entire mixture is suddenly vaporized. When it is suddenly vaporized, we call it a flash, right? By passing the feed from a high pressure zone to a low pressure zone. When definitely there is a pressure difference from high pressure to low pressure, then definitely that fluid or liquid is going to vaporize. Flash distillation is known as equilibrium distillation, such that separation is attempted when the liquid and vapor phases are in equilibrium. Remember, so vapor and liquid to be in equilibrium. Uh, this method is frequently carried out as a continuous process and does not involve rectification. So this is a process where we do not rectify the component or purify the components. So you can say you have the basic system for this. When a hot liquid mixture is
Sir,
allowed, yes,
sir, can I have a question?
okay.
सर फ्लैश डिस्टिलेशन की आपने बात की सर इसका समझ नहीं आया कुछ के जब एंटायर पूरा लिक्विड और जो गैस मिक्सचर है जब वो
I
एकदम
think we haven't finished
सर
flash
आप रिपीट
distillation
कर
yet.
सकते हैं
Maybe
सर आप
it's not finished yet. Maybe you're too early to ask the question, isn't? Let me finish flash distillation. If you couldn't
ओके सर
understand, definitely I'll do it for you. But let me
ओके
finish
सर
it first because we just started and your question is too early to that.
Sir, question है sir.
Let me finish this first, flash distillation, then we will be moving. I think it would be better if you ask your questions and note your questions and ask at the end of the lecture, because in between it might be difficult for you as well as me, uh, because it is actually it's not possible for me to answer all questions. The reason why, because I'm not sure who is going to talk, because there are several students and who has questions, and suddenly you two three questions are coming. So to whom I would be answering, right? If you have questions, definitely you can raise your hands, then we can answer your questions. Okay, let me first this flash distillation. I'll be asking, whoever has a question need to raise the hand and I'll be answering. Maybe we need to go one by one. Okay, let me finish this first, and then I'll be coming to your questions. Now, if we talk about principle, when a hot mixture is allowed to enter from a high pressure zone into a low pressure zone, the entire liquid mixture is suddenly vaporized. The process is known flash distillation, vaporization. During the process, the chamber gets cooled. The individual vapor phase molecules of high boiling fraction gets condensed, while the low boiling fraction remains as a vapor. Okay, so this is an equipment where you can see, your feed is pumped into a heater where you're going to heat up that feed, and then you have this, pressure reducing valve, and then when you lower the pressure, when this comes here, what happens is, now because this gets a cooling effect, now you already know that when you go from higher pressure to lower pressure, the effect of cooling, is activated. So what happens? I'm just giving you an example. Let's say I have a mixture of five different components, which is like C5, I have C6, I have C7, I have C8, I have C9. So these are some of the components. What I have done is I have heated this mixture up to a temperature of 80 degrees C. Just an example, right? Now, at that 80 degrees C, this one is it's a C5 temp boiling point is 50, C6 boiling point is 60, and I have given gradient of 10 degrees. So maybe up to 100 degrees centigrade for C8 and C9. Now, what happens is because you have pressurized that liquid by heating, if you're going to leave it, what happens is now those components which are already at high temperature than their boiling temperatures, especially that C5, C6, and C7. So they are at high temperature. Now what happened is other components which are whose boiling point is higher, like 90 and 100, they will definitely condense and they will come down. Those which has low boiling point will rise and go to the top. Now this is where you need to, this is where the separation happens. That's why we call it the flash distillation. Now what happens is you're going to get liquid, you need to process it further, and you're going to get, some of that vapor, condensate. If there are more than one component, definitely you are going to separate, because this is not a purification process. This needs rectification. This needs a further, you can say that, a separation, because this has just given in initial separation. Now maybe you have a range. For instance, you have a range of C5 to C8, right? Now this range is here. Now here maybe uh, from C8 to C10. So you know that this is a different range of component. This is a different range of components with respect to boiling. So this needs further separation, and this needs further separation as well. This is how a flash distillation works. Okay, now if you have questions, you can ask. Please raise your hand. I'll be allowing your questions. Okay, Sabi, what is your question? Please ask.
सर इसमें तो फिर आप एक कंपोनेंट को तो आप एक उसमें सीरीज में आप तो फिर सेपरेट नहीं कर सकते ना, आप तीन चार कंपोनेंट सेपरेट होंगे। अगर आपका 10 कंपोनेंट का मिक्सचर है उसमें से तीन चार ही सेपरेट होंगे, बाकी छः चार जो आप छः पाँच पाँच छः जो हैं वो आपके अलग रहेंगे, जो आपने रेंज इसकी टेम्परेचर की आपने सेट की है उसके हिसाब से। तो
Yeah, of course. That's what I'm saying. You
तो सर
cannot
फिर ये
rectify, you cannot purify. This is just a basic separation mechanism for different ranges of component you can do. In case if you have just two components and you have, boil them, like I have given you example from C5 to C10. In case if you have only C5 and C10, now maybe you can get higher purities. But still there are chances that those vapors can carry C10 with them. So still you cannot get 100% pure component at top, even or at the bottom. So this is
ओके
not
सर,
a rectification process, remember. I already
ओके
mentioned
सर,
this is not a rectification process. In
ओके
rectification
सर,
processes, what we do is we rectify components, we purify components. So this is just an initial you can say separation mechanism. Maybe
ओके
let
सर।
me show you one of the animations. I hope any animation is available on YouTube. Okay, I hope you can see my screen. I just want to show actually animation, but this is not a still animation. Okay. Okay. Okay, I'm unable to see, any animation related to flash distillation, but that's a very simple mechanism, right?
Okay, sir, leave it. रहने दें.
Okay. Okay, that's construction that already mentioned about this one. I hope that's clear. The feed pump is, I think I do not need to go its working mechanism because I already mentioned about those all equipment. So I'm leaving, those working principles, right? I hope it's clear. So I'm not going here. If there is any important thing, I will be definitely mentioning. The mixture is allowed for a sufficient time so that vapor and liquid portions are separate uh, and achieved. Yes, one of the things is that you need to give the time to that system. Operating conditions can be adjusted such a way that amount of feed exactly equals to the amount of materials removed. This one and other you can say precautions that you need to take. Vapor and liquid concentrations at any point remain constant in units. Yes, that's true. Uses, yeah. Now this is the thing that we need to go through. Flash distillation is used for separating components which boil at widely different temperatures. Right, I mentioned like where, like C5 and C10. Now there's a big difference. If we want to achieve bigger separation, if you can say purity, if they are very close, then that's very difficult for you, to get bigger purities. At this one, you cannot get the bigger purity. But for this one, definitely you're going to get bigger purities because the boiling point difference is too high. Okay, flash distillation is used for separating components which boils at widely different temperatures. It is widely used in petroleum industry. For refining crude oil, advantages flash distillation is a continuous process. That's one of the advantages you can say. Disadvantages, it is not effective in separating components at comparable volatility, right? I already mentioned it's difficult. It is not efficient in distillation when nearly pure components are required. Definitely, you cannot going to get pure components. We already mentioned this. Okay, now let's talk about vacuum distillation. Uh, Actually, vacuum distillation operates at reduced pressures, you can say. Let me give you an example. For instance, if we talk about the boiling point of water, normally at here in Karachi, you can see it boils at 100 degrees C. Okay, let's boil water, in Kashmir or in Gilgit or maybe even at that boiling point might be different. Have you observed that? Now, why that happens? Because we know that boiling point is actually is when vapor pressure of any system gets equal to the atmospheric pressure, then that component boils. Remember, right? Because vapor, the atmospheric pressure here in Karachi is very high. You can say 180, but at mountainous areas, at peaks, at elevated areas, because atmospheric pressure gets lower. When atmospheric pressure is lower, then components boil very easily. The same effect comes here. Now, if you need to reduce the surrounding temperature or the atmosphere or the environment temperature of that system. For example, let's talk about this one. Now this is a liquid. This is the it is atmosphere. We are not talking about outside the reactor. We are not talking about outside the column. We are talking about inside the column. If this pressure is lowered, right? If this pressure is lowered, definitely boiling point will also lower. So it totally depends upon this atmospheric pressure. Like if generally is 180 if you're operating at atmospheric pressure, but if you're operating at vacuum, in vacuum what we do? We use pumps or compressors to get that air out of that system so that a vacuum is created. So there is not air pressure inside. So what happens is when the pressure is lower inside, those components inside this system will boil at low temperatures. This is how vacuum distillation works. So what do you need? You need to have, but this is the assembly. uh, you need few things. Here is, a water bath, or you can say heating mechanism. You can heat by any system. Water bath a heating mechanism as well, because hot water can be used as a heating mechanism. So here must be the hot water. This is a flask, and this is a capillary tube. That's a thermometer to note the temperature. This is the cork, and this is the condenser. This is the uh, vacuum pump. Okay, now vacuum pump is added here. It is not. It does not mean that it reduces this pressure. Actually, what happens is it's reducing this pressure, because there was no other way to fix any you can say that vacuum system. And secondly, if you are going to put vacuum at other place, what will happen is it will attract molecules to itself, right? If we are putting up vacuum pump here, now molecules will be coming or traveling here because of that suction of the vacuum pump. So easily you can trap those molecules in the spot, or in the column, or in the vessel where you need to, collect them. So this is how vacuum distillation can work. Okay, let me go through some of its text. The distillation process in which liquid is distilled at a temperature lower than boiling point. I mentioned why lower, because boiling point get lower. Application of vacuum pumps, suction pumps, etc. are used to reduce pressure. Now definitely it's a reduction of pressure of the liquid surface. Distillation under the reduced pressure is based on principles of the simple distillation with some modifications. Let's talk about this principle. Liquid boils when the vapor pressure is equal to atmospheric pressure. Yes, we know that. uh, is if the external pressure is reduced by applying the vacuum, or the boiling point of the liquid is lowered. Yes, we already discussed that. Therefore, the liquid boils at low temperature. This principle is illustrated by using uh, an example of water. Okay, water boils at 100 degree, we know that. An atmospheric pressure of 1 atm, or 101 uh, kPa, or 760 mmHg. At 40 degrees C, vapor pressure of water is approximately 9.33 kPa. Okay, at this temperature, which is equal to 70 mm of Hg. Hence, external pressure is reduced to 70 mmHg, or 9.3 kPa, where the water boils at 40 degrees C. Now, that's just an analogous example. When your atmospheric pressure is 760 mmHg, right? What happens is your water boils at 100 degrees C. Now, if you are going to achieve, pressure at a lower temperature, for instance, if you lower this pressure to 70 mmHg, now at 70 mmHg your water can boil at 40 degree, because at 40 degrees C, the vapor pressure of that water are 70 mmHg. That's why if you are going to equal that atmospheric pressure to its vapor pressure, your liquid is going to boil. So this is one of the examples that you can, get to understand that how reduced pressure or vacuum pressure distillation works. Okay, the net results in the increase the rate of mass transfer into vapor. Okay, now this is another equation to understand that how vacuum distillation works. Actually, it is mass of the vapor formed, you can say. Okay, what equation is vapor pressure of evaporating liquid divided by external pressure. Now remember, actually we are talking about the mass of that component, that how much can it be achieved. We have two factors. One is vapor pressure, the liquid which is getting evaporated, and other is external pressure. Now what we are doing is we are dividing the vapor pressure of that liquid divided by external pressure. Now let's, see this example. According to this formula, water is allowed to evaporate at 40 degree and 9.33 kPa, which is 70 mm Hg of pressure. The mass of vapor formed in unit of mass is approximately 11 times. How? Like if we talk, of vapor pressure of that system, you can say that at 40 degree, uh, how much is it required, you can say. Actually it's 9.3 or 70 mm mmHg, you can say atmospheric pressure should be equal to that. If not, you cannot get it boiled. Or in other words, you can say at 40 degrees C, the vapor pressure of water is 70 mm of Hg. Now, because generally the vapor pressure should be 60 mmHg to get that boiled when your temperature is 100 degrees C. Now what we have done is uh, we have done the vapor pressure which is of the liquid water, at which actually it evaporates at 100 degrees C, which is 760 mm of Hg. But what happening is when you have reduced vapor atmospheric pressure to 70 mmHg, now you can see that how many times that rate of evaporation is increasing. If you see, it is 11 times. So you can get the figures right, that how the reduction of that surface or atmospheric pressure affects on the boiling rate or evaporation rate of any system, right? So this is one of the examples. uh, I think we already have seen this, that how assembly of the apparatus work. Okay. Applications. Normally what happens is when your components are very sensitive. For instance, if we have any component and its boiling point is 70 degrees C, just an example, maybe a biomolecule or protein or something, at 70 degree it is going to boil if we need separation. If you are going to boil that component or mixture at 70 degree, there are significant chances that it might get destructed, it might get destroyed or degraded, you can say, right? So you do not want this product to be degraded or destructed. So rather what you want is you want this temperature to be 30 degrees C, so that your compound, your product is not harmed. So it's at its ease, right? This is one of the basic assumptions to do, to carry out vacuum distillation, especially in pharmaceuticals and in food industry. Okay, here are some of the examples: preventing degradation of active constituents, enzymes, malt extract, pancreas and vitamins, glycerides, alkaloids, and there are so many other things that can be separated, which are temperature sensitive or temperature might degrade them. Disadvantages in vacuum distillation: persistent forming occurs. That's one of the difficult things. This may be overcome by adding capryl alcohol to the liquid or by inserting a fine air capillary tube in the second neck of the glass flask. To stream, the stream of the air is withdrawn and breaks the rising foam. Uh, the above method is not suitable for preparation of semi-solids or solid extracts by distillation under the vacuum. Okay, so this was about the vacuum distillation. I hope you have some questions. If you have any questions, please raise your hand so that I should answer and move on to the next heading. If you have questions, please raise your hand. Otherwise, I will be moving on. Abdullah, do you have a question?
Yes, sir, I have a question.
Okay, please ask.
Question is that, sir, as you said in the simple distillation, last point of application, we separate the one component on the basis of volatility. Then what's the difference between vaporization and distillation?
Distillation is one of the types of vaporization happens in distillation. You cannot distill it without vaporization. Okay, let's talk about the difference in vaporization and distillation. In vaporization, we do not need to collect the vapors. There's a no condensation mechanism, there's a no condenser. But when you're going to to condense those evaporated molecules, then we call it distillation. That's basic difference between distillation and vaporization.
Yes, sir.
Okay, are there any other questions? Okay, no questions. I think chat is going on. There is something. Voice cut के आ रही है. I'm not sure that why. जिनको मेरी आवाज ठीक आ रही है, तो प्लीज रेज योर हैंड. आई थिंक इट शुड बी ओके. और अगर कुछ के पास ऐसा है तो इसका मतलब ये है कि उनके पास नेट ठीक नहीं है. ओके, मेजॉरिटी आर रेजिंग हैंड. इट मींस दैट मोस्ट ऑफ देम कैन हियर मी वेल. तो इसका मतलब ये है कि फैजान साहब प्लीज आप अपना इंटरनेट चेक करें. ओके, लेट मी गो थ्रू प्रेजेंटेशन अगेन. Okay, now talk about molecular distillation. It is defined as the distillation process in which each molecule in the vapor phase travels mean free path and gets condensed individually without intermolecular collision. On application of vacuum, right? Molecular distillation is based on the principle of simple distillation with some modification. So this is the one major thing you need to know, that it is based on actually simple distillation. Okay, let me take my pointer again so that I can be using this for your help. This is called the evaporation distillation or short path distillation principle. The substance to be distilled to have very low vapor pressure. Examples are viscous liquids, oils, greases, waxy materials, high molecular weight substances. These boil at very high temperature. In order to decrease the boiling point of the liquid, high vacuum must be applied. So this is another thing that you need to apply high vacuum to those. The pressure exerted by the vapor pressure above the liquid is much lower. At very low pressure, the distance between the evaporating surface and the condensing is approximately equal to the mean free path of the vapor molecule. I hope you're aware about the mean free path of the molecules. Normally we call that molecule to molecule distance, but here we are talking about a single molecule distance. Actually, it's not about multiple molecules, because this is based on separate molecules. If you, I don't know, here might have gone through it. Okay, each molecule, right? So here we are talking about of the each molecule. We are not talking of the uh, intramolecular collisions. So here mean free path has a different concept than the mean free path in general. Generally, we say that molecule to molecule, distance or average distance gives us mean free path, right? But here we mean is like from one surface to another. Like this is a surface where you are going to vaporize your liquid, and this is the surface where you need to, condense that vapor. Now this is actually mean free path for such a system. Okay, molecules leaving the surface of the liquid are more likely to hit the condenser surface. Each molecule is condensed individually. The distillate is subsequently collected. Applications: molecular distillation is used to purification and separation of chemicals of low vapor pressure. Remember, normally it is used for the low vapor pressures. Purification of chemicals such as uh, tricrylyl phosphate, dibutyl, uh, what we call it, phthalate, and dimethyl phthalate. Uh, Okay, more frequently used in the refining of fixed oils. Vitamin A is separated from fish liver oil. Vitamins in concentrated by this method from fish liver oil and other vegetables. Free fatty acids are distilled at 100 degrees C. Steroids can be obtained between 100 to 200 degrees C. Triglyceride can be obtained from 200 and onwards. Proteins in gums will remain as non-volatile residues. Thus, above mixtures can be separated by molecular distillation. Requirements for the design of the equipment, the evaporating surface must be close to the condensing surface. That's one of the example, because your mean free path should not be too, high. So the distance between condensing and evaporating surfaces should be narrow. This ensures that the molecules to come in contact with the condenser as soon as they leave the evaporating surface. For this reason, this process is known as short path distillation. This is also the short path distillation. Okay, the molecular collisions should be minimized because they change the direction of the path of the molecules. In other words, intramolecular distances should be fairly high. Uh, it can be achieved under a very high vacuum, usually from zero point 0.1 to 1 pascals, which is of course very low. The liquid surface area must be larger as possible so that vapor is evolved from surface only, but not by boiling. Thus, this process is also called evaporation distillation. Remember, we're not, going to such a temperature where we need to boil that one. Rather, it should be vacuum-based evaporation. This is one of the examples. If you see that this one is a heater actually. Uh, this one is a condenser where this helps in collecting your molecules, and this one is a bucket. Okay, this is a vacuum pump, which is providing vacuum to that bucket. Uh, from here, you can see that if you're going to collect, you will have your residues, and this will have the product. Okay, this is definitely the feed. Okay, let's track that process flow. You can say, okay, feed has entered from this point and is going to this one at this position of the bucket, right? Now what you have done is, from here you have heated this one up. Now what you have done is you have put up a condenser. Now with the help of that condenser you are going to get some product, right? Or you can say, here they have mentioned it as residue, somehow you can say. Now there are two things. uh, you have gone through, uh, solutes and solvents. I hope. Normally, what is our definition for them? Generally, it is understood that solid crystalline thing or anything you're going to add in water, for example, salt. Salt is a solute in the water is a solid. But in actual concept, what we call a solute is, for a solution, solute is the component which is at the less quantity, right? And solvent is in the higher quantity. The any component which is in the higher quantity, we call it the solvent, and solvent is always in the less quantity. Similarly, we talk about the liquid extraction processes. We have raffinate and we have that extract. So extract can be sometime a product, sometimes extract is a residue. So residues are actually those part of the component which are in less quantity, which you need to remove, right? Now product is normally, you can say, generally, it's not always, is it normally in the small quantities. So it depends that how you're going to separate it. Either your product can be in vapors, either your product can be in the solids. So both can work. For example, here if you see examples behind. Okay, let me take you through this one. A triglyceride can be obtained at 200 degrees C onwards. Proteins in gums will remain as non-volatile residues. Now here proteins in gums are as the non-volatile which are remaining in the system, right? Okay, in this method, liquid feed is introduced to a vessel in which rotated at very high speed. If you see that, system, this is at high rotation. You can say it might be using a centrifugal force, and it has a centrifuge. On account of heating, vaporization occurs from a film of liquid on the other side of the vessel. The vapor molecules travel a short distance and gets condensed on the adjacent side, as we have seen in that equipment. Each molecule is condensed individually. The distillate is subsequently collected. Construction. It consists of a bucket-shaped vessel. We have seen that already. It has a rotated high-speed, uh, you can say that motor. Radiant heaters are provided externally to heat the fluid in the bucket. Condensers are arranged very close to the evaporated surface. Vacuum is connected to the entire vessel at the top. Provisions are made for introducing the feed into the center of the bucket for receiving the product and residues for recirculation. For receiving the product and residue for the uh, recirculation. Vacuum is applied to the entire vessel. I think we already have gone through this. Bucket shape, this. Okay. That's one of the other examples of molecular distillation, that how a molecular distillation can be achieved in equipment. So this is another equipment, you can say. Here you can see that a vacuum pump is connected to this one, and a rotation or motor is fixed at the top of that one. Here is product column. Here you can achieve your residues, and this one is a condenser. This one is a wiper, and this one is a jacket of that vessel or the reactor. We already mentioned this one about the rotor, and feed you have pumped from the top. Okay, this was about molecular distillation. I think we already have gone majority of the concept of this phenomena. Okay, if there are any questions, I'm taking you online here. Okay, if you have any questions, please ask, and then we'll be moving ahead. Okay, it seems there are no questions. If so, I'm moving ahead. Okay, let's talk about the steam distillation. Let's come to this equipment or processes. First, let us read about its concepts, that how it works. Steam distillation is a method of distillation carried out with add of steam. It means that you are going to add. Now here add is actually help, but adding steam, right? It is used to separate high boiling substances from non-volatile impurities, separate immiscible liquids. Examples: boiling point of turpentine is 160 degrees C. Now, boiling point of water plus turpentine mixture is 95.6 degrees C. At this temperature, vapor pressure of water is 86.2 for kPa, and turpentine is 15 kPa. Some of vapor pressure is almost 1 atm, which is normal atmospheric pressure, and thus high boiling liquid may be distilled with water at a temperature much below its boiling temperature. Principles: a mixture of immiscible liquids begin to boil when the sum of their vapor pressure is equal to atmospheric pressure. Yes, in case of mixture of water and turpentine, mixture boils below the boiling point of the pure water, uh, though the turpentine boils at a much higher temperature to that of the water. Applications used to separate immiscible liquids, for example, water turpentine, sorry, water and toluene. Okay, extraction at much lower temperature to protect from decomposition without loss of aroma. Extract volatile oils like clove, anise, and eucalyptus oils. Purification of essential oils like almond oil. Camphor is distilled by this method. Aromatic water are prepared. Limitations: not suitable when two immiscible liquids react with each other. Construction: metallic steam can be fitted with cork having two holes, safety tubes, blah 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 blah. Okay, I'm not reading this all. Let me take you through this equipment. Okay, actually here is the equipment, one of the equipments you may say. Uh, for example, you have water here. What you need is you need to have water or steam. You can use either of them. If you're using steam, you need to heat up this water. Okay, when you heated the water, you got the steam. Now you have here some of the leaves, you can say. If you want to extract some aroma, what will happen is vaporize water and essential oils. Now oils from these leaves hubs, you can say, will be extracted by using this steam. Now you will have some sort of condenser where you are going to get these two things, water and essential oil in hot water, definitely. Then essential oils can be taken in any vessel that you have. Okay, so this is basic or simple example of steam distillation, and this is another equipment, you can say. Again, this needs both things. This needs steam, this needs the components that you are going to have. For instance, this one has impure organic liquids, and you're going to create a steam here, and you're going to mix it with this one. When you're going to mix this one, their boiling point will lower, and then they will raise its vapors, and then you're going to separate by condense them, and then you're taking them to the vessel that you have. So this is how steam distillation works. So it's a very simple phenomena. One of the things that you need to note is that sometimes water is also used instead of steam. So it depends that how your chemistry is dealing with that specific hubs or whatever components, organic components you have in that system. But remember, there should not be any reactivity. If water or steam is reacting with that component, then definitely it is difficult for you to separate those components which you want to. Okay, I'm coming again to you guys. If there are any questions, please raise your hand. Okay, 4-1, what is your question? Zaki.
यस सर, आपने कहा कि सर स्टीम डिस्टिलेशन इमिजिबल के लिए यूज करते हैं, तो सर इसे मिजिबल के लिए भी तो यूज कर सकते हैं ना, अगर उन दोनों का बॉइलिंग पॉइंट डिफरेंट हो तो?
सेपरेट कैसे करेंगे?
तो सर जैसे फॉर एग्जांपल हमारे पास दो कंपोनेंट है, कंपोनेंट ए और कंपोनेंट बी। कंपोनेंट ए का हमारे पास बॉइलिंग पॉइंट लो है, तो अगर हम ऊपर उसे कलेक्ट करते हैं तो उसके साथ बी के मॉलिक्यूल्स भी होंगे, लेकिन वो लेस अमाउंट में होंगे, फॉर एग्जांपल 90% टू 10%। तो अगेन उसे रिफ्लेक्स के जरिए कर सकते हैं।
अगेन जो पर्पस है दैट्स नॉट अचीवेबल। नॉर्मली इस तरह को हम फिर एक्सट्रैक्टिव में आ जाता है। अगर ऐसा है तो फिर इंस्टेड ऑफ स्टीम यू नीड टू यूज एक्सट्रैक्टिव डिस्टिलेशन। आपको सॉल्वेंट यूज करें, एक्सट्रैक्ट करें, देन बॉयल करें। ठीक है ना? यहाँ पे तो हमारा पर्पस ही ये है कि हम सेपरेशन चाह रहे हैं ना। हाँ, तो इस वजह से हम इमिजिबल को ज्यादा वो करते हैं। एनीबडी एल्स? Okay, seems no questions. No questions can be sign of a good and sign of bad at the same time. Okay, so I'm leaving up to you that what do you think of it. Okay, let's talk about destructive distillation or dry distillation. Distillate is decomposed product of constituents of organic matter burnt in absence of air. So this is the one thing that you need to know, that it is conducted in absence of air. Not used in lab practices. Of course, it is difficult to do that. Involves the heating of dry organic matter in suitable vessel in absence of air until all volatile organics are driven off. The distillate is the decomposition product of constituent, because it's actually a solid. If you're going to do it, it will definitely decompose. Wood distillation industry and coal carbonation industry provides many useful materials with this method. Okay, that was just simple thing. Okay, now what happens is sometimes we have solids, for example, you can say asphalt, one of the examples I'm giving you, or some heavy components, maybe coal, right? Now what do you want is you want to convert that solid organic compound into liquids. Normally we do it with two things. One is we call it the pyrolysis, right? I hope you have written about that one. This is a process where high temperature is applied to the mixture, a solid mixture, in absence of air. We call it pyrolysis. So that dry distillation can be one of the types of pyrolysis. Another is thermolysis, right? In thermolysis, definitely we apply a lot of temperature into it, but we do not fix it with absence of air. There
अबे
can
भाई
be
ये
air,
तेरे को
there can
पता
be water
है,
as
ये
well.
मुझे पता है, ये अहमद को पता है, लेकिन बाकी को तो नहीं पता ना।
जकी कोई मसला है? ये नहीं, अगर क्वेश्चन है तो पूछे. इज देयर एनीथिंग दैट आई कैन डू फॉर यू? ओके, लेट मी म्यूट यू.
इससे
आवाज क्लियर नहीं आ रही. शुजात, वाई? आई थिंक बाकी सबको क्लियर आ रही है. ओके, आई एम आस्किंग वंस मोर. मेरी आवाज ठीक है? प्लीज रेज योर हैंड. ओके, मेरी आवाज ठीक है, इसका मतलब है कि शुजात आपके
बिल्कुल
नेट में
सर,
मसला है. प्लीज
लाउड एंड
डू इट
क्लियर।
राइट.
2G इस्तेमाल कर रहे हूँ बच्चे।
ओके, दैट्स फाइन, चलता है. ओके जी, वी आर मूविंग अहेड. अब ठीक है, आवाज ठीक है मेरी, एंड वी आर मूविंग ऑन. तो अगर कोई क्वेश्चंस हैं रिलेटेड टू ड्राई डिस्टिलेशन, प्लीज यू कैन आस्क, देन वी विल बी मूविंग टू नेक्स्ट हेडिंग. मोहम्मद रहीम बख्श, क्या क्वेश्चन है आपका, या आप आवाज बताना चाह रहे हैं? आपका हाथ उठा हुआ है. ओके, कोई
आवाज के
क्वेश्चन
लिए
है? अच्छा, आवाज के लिए. अच्छा, कोई क्वेश्चंस नहीं है ड्राई डिस्टिलेशन के हवाले से या फिर डिस्ट्रक्टिव डिस्टिलेशन के हवाले से? देन वी कैन मूव ऑन.
सर, ये डिस्ट्रक्टिव के लिए सुना था कि हमने ये सॉलिड की के लिए हम सॉलिड की डिस्टिलेशन के लिए हम इसको डिस्ट्रक्टिव डिस्टिलेशन यूज करते हैं।
तो मैंने भी तो यही कहा है.
अच्छा, तो आवाज कट गई होगी मेरी।
आवाज कट रही होगी.
अच्छा,
ओके, संदीप, व्हाट इज योर क्वेश्चन? संदीप.
सर रेज हैंड किया था वॉइस के लिए बस।
ओके, तो हाथ हटा दो ना भाई. अच्छा जी, let's move to the next heading. That's actually compression distillation. Compression distillation method was developed to meet the need for Navy and Army for fresh water from sea. Okay, बेटा अपना माइक बंद कर दें. ओके, प्रोडक्ट. हमारी क्लास में कोई छोटा बच्चा भी है क्या?
जी सर, अजहर है सर, अजहर नाम है।
अच्छा,
सर 3-4 हैं, एक नहीं है।
as a product obtained is quite pure and pathogen free. There is a lot of there for. बेटा आप क्लास ले रहे हैं? Okay, meets the requirements of pharmaceutical industry. It is economical from the standpoint of consumption of fuels in water. The feed water is heated in an evaporator for boiling. The vapor produced from tubes is separated from the entrant distilled end in separator. The vapor is then conveyed to compressor, which compresses and raises its temperature to 118 degrees C. Then it flows to the steam in chest, where it is condensed on outside surface of tube. During the condensation, heat is released, which is allowed for heating of fresh feed of the tube. The vapor condensed and drained off as distillate. Okay, I think this might be a little difficult for you to, get through that what I have talked, because more of the text. Actually, if we see the concept that how it has been developed, actually this is developed for Army and Navy. I'm giving you why, because normally Navy, they remain in sea, right? You know that. When they remain in sea, it is difficult to get the fresh water. So to desalinate water, what mechanism there is used is, what they do is they heat up the water, right? When they heat up the water, that water gets converted into the vapors. Now, those vapors are compressed, you can say. Those vapors are compressed. That compressed vapor is used for desalination water or drinking water, you can say. That's why we call it compression distillation. Here, the compression concept is coming from the compressed, you can say, steam, right? Because they have generated the steam using whatever heating mechanism, and from that compressed steam, they are desalinating the water, right? So that's actually the basic concept. Fractional distillation, I think most of you know about the fractional distillation. Uh, Let me get you through some of the text. This method is known as rectification because part of the vapor is condensed and returned as a liquid. In fractional distillation, actually there's not only rectification, but there is stripping as well. I think last time we talked about. Normally the top section is called the stripping, in the lower section, sorry, top section is called the rectification, and lower section is called the stripping. In fractional distillation, we take fractions of different compounds. It means that it must have multiple, you can say, components in a mixture. Okay, if we talk about rectification, what we do in rectification is we take out the product from whatever plate or whatever cut we have for it, and then we pass it through a condenser. So we partially condense that liquid. We take some of that as reflux and other as a product, right? So this is how fractional distillation works. So distillation mechanism is still same, but because we are going to take some fractions of those, you can say that products, that's why we call it fractional distillation. Fractional distillation is process in which vaporization of liquid mixture gives rise to the mixture of constituents from which desired one is separated in the pure form. I think in last lecture we have a detailed discussion that how they give rise to a component, right? How these vapors which come from the reboiler, how they react, not react actually, how they behave with other components, how a temperature profile is created within a column. So this is all about that column. Let's talk about some of the differences in simple distillation and fractional distillation. In simple distillation, vapor is directly passed through the condenser. That's it. Okay. In fractional distillation, the vapor must pass through a fractionating column in which a partial condensation of vapor is allowed to occur. So this is actually partial condensation, some as product, some as reflux. Okay, condensate is collected directly into the receiver. Condensation takes place in fractionated column, so that part of that condensing vapor returns to the still. So this is how we do it. When a liquid mixture is distilled, the partial condensation of the vapor is allowed to occur in fractionated column. In the column, ascending vapor from the still is allowed to come in contact with the descending vapor, returning to the still. We in last lecture we totally discussed that how we talk about descending vapors and ascending, you can say that liquid, or descending liquid and ascending vapors, that cascade we talk of for multiple number of plates. This results in enrichment of vapor in the more volatile component. Yes, this is why we can say that we purify or enrich components by condensing the vapor and the reheating liquid repeatedly. I already mentioned that we do two things in the fractionating column. So we condense and we reheat. For condensing, we condensers. For reheating, we use reboilers. Okay. Equilibrium between liquid and vapor is set up at each stage, or you can say at each plate. That's again the same thing that we discussed previously. Ultimately results in the separation of a more volatile component. So this is how this is going to help. Application fractional distillation is used for the separation of volatile miscible liquids with near boiling points, such as acetone in water, chloroform in benzene. What are disadvantages? Fractional distillation cannot be used to separate miscible liquids which form pure azeotropic mixtures. Yes, for azeotropes it is difficult. Okay, I think many of things we already have discussed, so I'm not going in detail that what it is actually. Okay, now talk about some of the columns that we use. We normally use two types of columns, in major. One is packed column and other is plate column. Uh, this is still a rare, this one. Packed column is more for, absorption normally, but plate columns are very common for distillation purposes, right? Okay. Uh, Here you can see some of the different shapes of packed columns. One you can see with the pear shape. This is one shape. Another is a rod and disc type. It will have rods and discs, and it. We're not talking here more about packings, that how they do, because I remember about pack columns we had some detailed discussion in previous classes when we went through absorption chapter. So I hope that you already have lots of concept about pack columns. So I'm not talking much of it here, right? But the plate columns, I think we also have some discussions that how plate columns are used and what type of pack columns we might have. Here is one of the examples. You can see that these are the different plates. This is its interior view, you can say. But there can be several types. Bubble cap. This one is a bubble cap type, and this one is a sieve tray, and then we have valve trays and other types of trays as well. Okay, this is a bubble cap here, you can see. Okay, so still I think we're not talking much about these trays. Okay, we already have talked about, I think, vapor liquid equilibrium, that how a vapor liquid equilibrium exists on different plates. So this is all about vapor liquid equilibrium composition. I think we have talked about with respect to temperature. We also have talked about this with respect to pressure. So we already have you can say pxy diagrams, and we already have txy diagrams. So these both are discussed in very details. I think we discussed those in absorption. Okay, this is again the same thing. Last is azeotropic in extractive distillation. In azeotropic, okay, if there are any questions, let me answer your questions, then we move on. Any questions, please, on fractional distillation? If not, then we are moving to the next heading. Okay, there seems to have no questions. Okay, that's good. We are moving to the next. Okay, azeotropic distillation, in which azeotropic mixture is broken by addition of a third substance, which forms a new azeotrope with one of the components, right? So let's talk about azeotropes. Actually, azeotropes are those mixtures. We call them that they do not have bigger differences in their boiling points or volatilities. So their relative volatility actually overlaps, you can say. When overlaps, it means, for example, if we have two mixtures like A plus B, right? If we are going to separate them out, now maybe I need to separate 70%. Now 30% I might have overlap of B. Now still there's no purity, right? Similarly, if we talk of this one, same will be for this one. If 30% is going there, it will have 70% itself. So in case that can be one of the examples, like 30-70% is overlap. So 30% would be the overlap in between these two. So actually we cannot separate them or purify them, simply we can say, without any means. So what we do one thing, Like if we have these two components A and B, what we do is we add a third component C. Now this C comes in and lowers or rises vapor pressure of both of these. Now maybe this one or this one, it depends on the chemistry that you are using as a drop for which one. When this makes an as drop, if right, so what will happen is there will be volatility difference. For example, I'm giving you an example. At 80 degrees C, it has a vapor pressure of you may say 500 mmHg. At the same temperature, it has a vapor pressure of 5 450 mm of Hg. Right. Now there is difficulty in separation. If you are adding that third component, now it has two things. Either it will lower or rise vapor pressure of one of these. Now if we are adding for this one, this must be a component which should rise its vapor pressure because it's already high. For instance, if I'm adding any component which rises its vapor pressure to maybe 600, 700, whatever that value might be. Now here would be now a bigger difference for separation. Now this will make it easy for it to be separated, right? So this is how we do with azeotropes. Now because we already added that third component, now what we need to do is we have to separate that third component. The third substance added to the azeotrope mixture is relatively non-volatile liquid compared to the other to be separated. Okay, isotopic distillation, constant boiling mixture of a special composition for giving minimum or maximum boiling point than individual components with minimum or maximum boiling point respectively. So this is how we do it. An extractive distillation, definitely, because we have added another component, then we need to extract it. Now maybe I need to give it further explanation that how this extractive distillation can happen. Okay, the screen is okay. Let me take a pointer for you, or not this one. Okay, let me take a pen for you. Now, for instance, I had this one component C, which has somehow extracted A or tempered with A. Now I need to separate it. Again, what I need to do is I need to distillate it, right? I'm giving you another example of extractive distillation. What happens is we extract sometimes oils. I'm giving you a simple example. For example, if you're talking of bean oil, right? If we have some beans and we are taking their oil, we need to use any solvent, maybe hexane, maybe ethanol, maybe propanol, maybe acetonitrile, whatever. Now it will attract or receive extracted oil. When it has extracted oil, now it has that solvent as well. Now it is a mixture of oil plus solvent. Now this is actually called extraction. You remember that one, right? Now this extract to be this you can say that distilled. Now this would be extractive distillation. So it has actually two things at the same time, extraction as well as distillation. First is extraction, it is followed by distillation, but both are different concepts. Extraction is different, distillation is different, but they happen step by step. You cannot say they happen simultaneously, they do not happen simultaneously, happen one after other. But first extraction or isotope, then distillation. Same thing is for the upper one, that you have added C. Now C should show its effect, then you need to distillate it. C has already tempered with A. Now its boiling point is different than what it was. Its density or vapor pressure is different than it was. Okay, that's all about distillation, major things that we have gone through. Now if we have questions, please raise your hand. I'll be answering one by one those questions, and then we will be finishing or concluding today's class, and we'll be meeting in next class. Yes, are there any questions? Zaki, yes.
यस सर, सॉरी उस टाइम माइक ऑन रह गया था मेरा। मैं ये कह रहा था सर, ये जो डिस्टिलेशन में थर्ड कंपोनेंट ऐड कर रहे हैं जो वेपर प्रेशर को इंक्रीज कर दे रहा है, ए और बी के दोनों में से किसी एक के वेपर प्रेशर को इंक्रीज कर रहा है, जिसके बिना पे हम सेपरेट कर रहे हैं ना, तो सर ये उसकी रिएक्टिविटी पे डिपेंड कर रहा है कि ये ए के वेपर प्रेशर को इंक्रीज करेगा या बी के?
डेफिनेटली उसकी जो आप ये कह लें कि रिएक्टिविटी या उसकी जो पोलैरिटी है किसके साथ है, पहले हम केमिस्ट्री डिफाइन करेंगे कि हम चाह क्या रहे हैं, उसके बाद ही हम ऐड
और
करेंगे।
ये एक्सट्रैक्टिव में जो ऑयल और सॉल्वेंट की बात की आपने, ये दोनों भी तो इमिजिबल है ना, तो इनको भी हम सिंपल उसके जरिए स्टीम के जरिए भी कर सकते हैं।
लेकिन हम तो यही कह रहे हैं ना कि पहले हमने एक्सट्रैक्शन की, उसके बाद डिस्टिलेशन की। पहले एक्सट्रैक्शन फिर सिंपल डिस्टिलेशन यू कैन से, बट सेम टर्म हम यूज करते हैं एक्सट्रैक्टिव डिस्टिलेशन, क्योंकि दोनों प्रोसेसेस पैरेलल आ रही हैं इसके। अगर आप इसको सेपरेट देखेंगे तो आपको सिंपल डिस्टिलेशन नजर आएगा, ठीक है ना, लेकिन क्योंकि एक्सट्रैक्शन हुआ है, दैट्स व्हाई वी कॉल इट एक्सट्रैक्टिव डिस्टिलेशन। ठीक है जकी, इज दैट ओके?
सही है सर। सर इतने
Okay.
सारे टाइप्स पढ़ा दिए, काफी चीजें मिक्स हो रही हैं बिल्कुल।
तो बेटा आपका काम है ना बाकी जाके किताब पढ़ना, मैंने तो अपने तरफ से पढ़ा दिया। डिस्टिलेशन का मैं आपको पूरा एक बुक दूंगा, एक बुक नहीं तो एक चैप्टर पढ़ लें उसका। ओके, एनीबॉडी एल्स, कोई और क्वेश्चंस हैं? या तो ज्यादा समझ में आया या तो बिल्कुल नहीं आया है।
सर काफी हद तक आ गया बाकी हम YouTube चेक करेंगे तो फिर बाकी सारा के सारा आ जाएगा।
ओके,
ओवरलोड हो
तो
गया है।
सब समझ आ गया सर, सब समझ आ गया।
अरे वाह भाई, आप जीतते हो। आप कहाँ हो कप्तान साहब?
सर आ गया, कराची आ गया सर।
अच्छा, ऑनलाइन क्लासेस थी, आप घर बैठे भी क्लास ले सकते थे, कराची आना लाजमी तो नहीं था।
वो अम्मी अब्बू ने आना था ना कराची वापस, इसलिए।
अच्छा चलिए ठीक है, और कोई क्वेश्चंस हैं?
सर बता, मेरा सफर कर रहा है पाकिस्तान जाके, मेरान में सफर कर रहा है पूरे पाकिस्तान का।
क्या कर रहे हैं?
मेरान गाड़ी में पूरे पाकिस्तान का सफर कर रहा था साथ।
That's good, that's good. Okay, अगर कोई क्वेश्चंस नहीं है तो आई थिंक दैट्स इट, वी आर वाइंडिंग इट अप, और नेक्स्ट क्लास में इंशाल्लाह मिलते हैं फिर मंडे को। इज दैट ओके?
यस सर।
ओके सर, थैंक यू, थैंक यू।
ओके जी, थैंक यू, अल्लाह हाफिज।
अल्लाह हाफिज। सर अल्लाह हाफिज। ओके, अभी इसकी क्लास है, सर की क्लास है।
सर मजार इमाम को चेक करना है तुम लोगों को।
ये मीम शेयर करना हो, ये मीम शेयर करना हो सारे मैसेज में, चैट पे।
क्या
चैट का बच्चा को इंसान तुम सच चूती है।
अरे इजलाल
सच चूती है रंडी कंजर बड़वा।
इजलाल भाई,
लाला हल्के में आ।
ये सवाल
क्या हाल है सर का? ठीक ठाक यार, आवाज ही नहीं आ रही यार।
खैरियत, तुम सुनाओ।
यार सितमगार,
आवाज ही नहीं आ रही यार इधर।
आवाज आ रही है ना, हमारी नहीं आ रही क्या? पहचानो, अरे दीवानो, हमें दोन।
इजलाल गिलगित में है क्या?
भाई तोते किसने पाले? तोते
सुनील,
हाँ
चल आजा मिशन पे।
हाँ
शुरू हो जा मिशन पे, 12 बज गए।
चल उसमें आज जानो, मेरे ख्याल से अभी
फ्यूल एंड कंबशन।
हाँ
फ्यूल एंड कंबशन।
ठीक ठीक है ठीक है ठीक
ओके
है यार
ओके ओके